19. We're going to do the first part of chapter 19 now in front of chapter 13. And then the second half of 19 we'll do later in front of and with chapter 20. Okay, so the first part of thermodynamics is spontaneity. Okay? If you take an egg and you drop it, then the egg cracks all over and you end up with a mass. So we have our mass here, okay? But if you'll notice, this direction is spontaneous. This is not. You don't take eggs that are broken and immediately go back up, okay? This is ice water. And the question is does ice form spontaneously? It does in the freezer, but it doesn't. It melts if you're above 0 degrees C. So what we're saying here is that whether something is spontaneous or not is a function of what conditions you put it under. For example, okay, gravity would make the eggs fall down, but if you were playing with eggs on the moon, they wouldn't fall down, they'd go up. So they might not break. Whereas, freezing water is a function of what the temperature is that you've got it under. Okay? So what is a spontaneous reaction? So for example, we've got hydrogen and oxygen spontaneously does form water. But by definition, a spontaneous reaction is one that proceeds on its own without any outside interference. Okay, without outside interference. For example, if you've got a ball balanced on something and you push it, then it can't be spontaneous. Because if you do something to it to make it go or react, etc., then it is not spontaneous. So anything that will go on its own, balls rolling down a hill, etc., without anybody messing with them, it is spontaneous. Okay? Now, the opposite direction for any spontaneous reaction is non-spontaneous. And you're like, wait, that was pretty obvious. Well, that is true. But what we're going to see is some reactions will proceed in both directions. So they may be favored for one side, but there's no direction that's spontaneous. But there are other directions, other reactions that are spontaneous only in one direction. Okay? Because for equilibrium, both directions will proceed at the same rate. That's the definition of equilibrium, is they proceed at the same rate. So there's no such thing as spontaneous if you're dealing with an equilibrium. Okay? So when we talk about a reaction, we're going to talk about whether it's spontaneous as written or non-spontaneous. Okay? So, reversible reactions proceed in both directions. These are the ones that form an equilibrium. Okay? And remember, when I say directions, I mean reaction to favor. Okay, irreversible reactions proceed in only one direction. For example, if you take magnesium metal and burn it, you'll form magnesium ash. Once you start that process, you have to give it enough energy to light it on fire. Fireworks. Sparklers, my favorite. Then that's a one-way process. Once you have burned all the magnesium, you can't get it back. Okay? Unlike reversible reactions, where if you move it to the product side, you can move it back to the reactant side. Now, reversible and irreversible reactions give directionality. That is not the same as spontaneous, because when we say it's a directionality, it can go one direction or the other. That has no bearing on whether it's going on its own or not. Okay, so these are totally different things. So back in chapter 5, we did, this is 12:12. So back in chapter 5, we talked about thermodynamics in 12:11, and you talked about endothermic reaction process, and those are the ones that require energy. So delta H is greater than zero, so delta H is positive. So those reactions are spontaneous from the form of energy. These are not spontaneous. Okay? Exothermic, on the other hand, delta H is less than zero because it's negative, because it's going to give off energy. Kind of doing this in reverse order, sorry. But spontaneous reactions from the energy or enthalpy standpoint are exothermic. So what we say is energy is not needed, it's given off in an exothermic reaction, so that's the spontaneous direction. An endothermic reaction requires heat, so that's something has to be done in order to move it forward. Okay? So this brings us to the first law of thermodynamics, aka the law of conservation of energy. And if you remember back, and I know you slept since then, so you probably don't, we've done this before, but this is similar to the law of conservation of matter, and it says energy cannot be created or destroyed and just like matter, it's only converted from one form to another. So when they talk about solar energy or even wind energy, the way it works is we'll do solar. You're taking the energy from the sun, the radiant energy, and then you're changing it into a usable electricity for people. So what you're doing is you're taking one form of energy and converting it to another form of energy, but you didn't make energy, nor did you destroy energy. So that's the other thing is energy always goes to another form. So if we have iron here reacting with oxygen, we produce iron 3 oxide, which is more commonly known as rust. Okay? So if you look at it, it has a delta H value that's negative, and it's actually a pretty big negative. So is it spontaneous as written? And the answer is yes, because according to thermodynamics, it is exothermic, which energy-wise, that's spontaneous. Okay? So then that brings us to the next question, is we have ammonium nitrate, which is a solid. We add it to water. And the first one is a reaction. The second one's a process. And both of them involve chemicals. So it forms the aqueous solution. And it has a delta H of 28.1. Okay? And so the question says, is the process spontaneous written? And the answer obviously is yes. Ha ha ha. No, it's not obvious because you're like, wait, this says no. And it does from an energy viewpoint. But you know what this reaction is? This is an ice pack. If you've ever been out playing sports and you or somebody else twisted something and you go get the little ice pack and you smack it, it's got those white lumps in it. Sometimes it's powder, sometimes it's little beads. And you either break a bag or you hit something, etc., and then it suddenly gets cold. So what that tells you is that once you mix them, and you're like, but you're doing something. No, you're actually artificially keeping them separate. When you allow them to mix, and that's all you're doing is mixing them, when they come together, then yes, the ice pack will go cold, and it spontaneously dissolves as it does this. So this reaction, according to enthalpy, is not spontaneous, but it occurs. So the question becomes, why does ammonium nitrate dissolve spontaneously? We know that energy is not favored because delta H is positive, so there's something else. The question is what is that something else? Well, that is something else is entropy. Now, guys, I'm going to tell you right now, enthalpy and entropy sound very similar. And since I'm doing this on a recording, it may be hard to hear sometimes. So pay attention to what I write as opposed to what I say, because also I've been known to say it wrong. And I'm trying not to do that here, but it occurs. Okay. So entropy is the measure of randomness. Okay. And we really call this disorder. So what we're doing is we're looking at how disordered or random a system is. Okay. Now delta S is a state function. And remember, state functions are path independent. So it's path independent. We don't care how you get from point A to point B. We just need point A to point B. And remember, delta H is also a state function. Remember, state functions are capital letters. Okay? So when we talk about order or entropy, we're talking about order or disorder or randomness of a system. And actually, it should be randomness as opposed to random. Okay? More about that as we go. So a closer look, the entropy change when a gas expands isothermally. And then that brings us to the second law of thermodynamics, which involves directionality. So what it says is for any spontaneous process, the entropy, delta S, of the universe must increase. So what this does says that when you have a spontaneous process, it may be non-spontaneous on the local, but it may be more random on the universal scale. And remember back when we did thermodynamics in chapter 5, we talked about the system and the surroundings and the energy is moving back and forth. Well, it's the same thing here. What we're looking for is, remember, we want the change in entropy for the universe to be zero, greater than zero, for spontaneous reactions. So we need it to be positive. Now, remember, enthalpy is spontaneous if it's negative. Entropy is spontaneous if it's positive. So don't forget that. So what happens is that the change in entropy of the universe has to equal the change in entropy plus the change of the system plus the change in entropy of the surrounding. Okay? And remember, if we are positive, we're increasing this order. This is favored. And if we're less than zero, we're decreasing this order, which is not favored. Okay? So the bottom line is sometimes you may have a reaction that is not spontaneous one way, and it ends up being spontaneous because it has another effect. So, for example, let's think about our ammonium chloride. Delta H said that it was positive, so that would be non-spontaneous. But if we look at it, and remember, here we have sodium chloride, which is table salt, and ammonium nitrate is also a salt. Notice that when we put it in water, it starts to separate, the ions separate out. So you're going from one particle up to two particles, and the one particle is localized. This is the solid, whereas the ions are all over. They're free range, all over the solution. Okay, so what's got more disorder? All over the solution. Okay, so in 1877, Ludwig, and again, I don't speak German, so I'm sure I'm mispronouncing that. Boltzmann proposed a relationship between entropy and microscopic states. Okay, so he said entropy is equal to K, which is Boltzmann's constant, times the number of the microscopic disorder of the microscopic states. Okay, so entropy is the measure of the number of microstates associated with a particular process. So, for example, different processes will have different numbers of microstates. Now, microstates are really not that bad to look at. They're actually pretty easy. And if you're in Dr. Knuckles' class, she's probably going to spend quite a bit of time with this. But all I want you to do here with Boltzmann's relationship is to understand that entropy is related to the microstates. Okay, you can relate it to work using Boltzmann's constant and the initial and the final work done. Again, know that you can do this. I'm not going to get this one, okay? But I am going to look at factors that affect the disorder. All right, so first thing is the number of species present. As you increase the number of species present, you increase more disorder. As you increase the volume or the spatial arrangements, you get more disorder. And the last one, which is actually kind of the one of last resort because it's the least amount of randomness, is the molecular motion. As you increase temperature, you increase the molecular motion. So temperature actually plays a huge effect if it's a gas, but if it's a liquid or a solid, it's not as important. So when I said it's not as critical, it is for gases, but not for liquids and solids. Okay, and remember, the temperature is the measure of the average kinetic energy of the atoms, molecules, or ions, whatever you're looking at. Ions, particles, whatever they are, of a substance. So, as the temperature increases, the energy increases within the molecule. Now, these are relatively simple if you think of them in terms of just simple items. For example, the number of species present. So think about herding cats. That's one of my favorite examples because cats don't herd well. They are not herd animals. So if you're trying to chase one cat, big fat deal. If you're trying to chase multiple cats to get them all in one area, then that becomes much more of a challenge. And you can herd puppies, kids, toddlers, whatever you want. Same thing with the number or the number of volume and spatial arrangement. Again, try to catch a cat in a small closet. No problem. Move to the big living room. No furniture. Move to outdoors. As you increase the volume, it is much harder. And then molecular motion. Things that stay still are easier to grab. If they're in constant motion, it's much harder to grab them. So, keep these in mind, is really simple. So, we've got 4 identical spheres in 2 containers that are separated by one little tube. We're going to call these microstates or spatial arrangements. And if we're dealing with arrangements, 4 particles, and here's the trick, they're all the same. So we have 4 particles, we have arrangement of 4 to 0, 3 to 1, and 2 to 2. Now, somebody might say, wait, but we could put 1 and 3. No, that's the same as 3 and 1. We don't care left and right. We only care that we have 3 on one side, 1 on the other side. So, what we have is 3 arrangements. So you're like, okay, that's easy to see, no problem. Now let's do it again. Except this time we're going to have 4 different species. So when we have the arrangement with all 4 on one side, none on the other, we only have 1 arrangement there. We only had 1 arrangement before. But now notice we have the 3 and 1. We've moved from 1 option to 4 options because we can isolate each color. Now, if we go to the 2 and 2 arrangement, we can isolate the options. So we went from 1 option to 6 options. So the total is we have 11 arrangements if we have 4 species that are different. So we went from 3 that were the same to 11 that are different. So this has a huge effect in terms of your randomness if your particles are different. The other factor is remember we talked about temperature, motion, etc. has a huge effect if we're talking gases or liquids or solids. Liquids and solids, remember, we call these condensed states. Because while they occupy space, it's much more limited, whereas gases will occupy the container. It doesn't matter how big the container is, it goes all over. So what ends up happening is if you think about it, you have a lot more disorder here than you do here in the solid. As a matter of fact, the solids are much more restrictive. So what we end up finding is the entropy of a solid is, and actually, I got one too many here. Okay, the entropy of a solid is less than the entropy of a liquid. But liquids have much less disorder than do gases. Notice that gases have a huge effect. There's not really a lot of difference. There is a difference, but not a huge amount between liquids and gases. Liquids and solids. But gases are hugely different. So the question is if you're a solid, do you have any option at all? Actually, yes. Because if you're not moving in terms of position, you're in a crystal, you still have a variety of molecular motions. So these are the ones that cause the least disorder. These basically, you're sitting there taking notes. Yes, you're sitting in a chair, so you could be a solid, but your hand is moving. So you have some motion. So if you have a molecule, in this case we could use water here, what you're seeing is you're seeing vibrations on this bond here. They can go in the same direction. They can go in opposite directions. They can be wagging in between here and there. These are different vibrations. This is a rotation. So if you're a top and you're spinning in place, that would be a rotational energy. And yes, that has some randomness because if you spin a top and it's got like a dot on it, then if it spins really, really fast, the dot seems to be a solid line. So it has disorder there. The third one is translational energy. And this is the energy basically of moving it through a distance. Now, this is kind of a fun slide for me because when I'm in front of everybody, I wave my hands, rotate around, and move across the front, showing you that as a particle, I can show you these molecular motions. And again, these are the least amount of disorder because they're all kind of in place. But if nothing else has an option, you take this. Okay? So here's the question. For each of the following pairs of substances, which substance has the greatest delta S? So if we look at it, we have N2O and we have helium. Now we have 0 degrees K and 10 degrees K. So remember, as you increase the temperature, you increase the energy, which means you also increase the disorder. So in this case, if I'm asking for the greater disorder value, and I could be asking for the least, but in this case, the answer would be helium because it has a higher temperature. Okay, so here we go again. We still have N2O and we have helium, but we're occupying the same temperature and pressure. So what the pressure means is we've got the same volume. We've got the same temperature, which means we have the same energy. So that's no help. So we don't have a difference in number. We're assuming that we don't. We don't have a difference in volume. So the only difference we have is we have to look at molecular motion. Well, and you can think of this as it happens to have a double bond oxygen, but you don't have to know that, versus helium. Well, guess what? Helium is a point in space. So it really has nothing other than rotational energy, whereas this one has all of the vibrations associated, and the rotation would be much more interesting, etc. So in this case, it's not a huge difference, but N2O will have the greater entropy. Okay, so now here we go. We have water. And water. And notice that this one is a liquid. This one is a solid. Our temperatures are the same, so we can't differentiate there. So all we've got is the crystalline structure. And we know that the entropy of a liquid is greater than the entropy of a solid because there's more movement associated with the liquid. So therefore, H2O liquid would win here. Okay? So this is simple if you're looking at two compounds. Well, we'll take it a step farther and we will look at it with respect to equations and reactions. And this gets a little more interesting because we have to look at a variety of things. The assumption here is they're all pretty much the same temperature, so we can throw that one out. So if we look at it, our answer is going to be delta S is positive, negative, or can't tell. And can't tell is not as common, and you still have to specify what's what. So if we look at it, we have 1 mole of particles here. How many moles of particles do we have on the product side? Well, if you guess 2 moles, you're correct because it's aqueous. That means it's split up into silver ion plus nitrate ion. Okay? And if you look at it, this is a solid and this is a liquid. So in this case, we're moving from 1 mole to 2 moles. So we increased our number, and we're moving from a solid to a liquid, which means we increased our S, increasing the number, increasing the S's. So in both cases, both of these increase the entropy. So we have delta S is positive. That's all you do to work these. We'll work at another one. So over here we have 1.5 moles going to 1 mole. We have 2 gases going to 1 liquid. So delta S here is going to be negative because we're moving 1.5 to 1 moles. So we're decreasing entropy. And then we're moving from the entropy of a gas to the entropy of a liquid, which means we're decreasing entropy. Since both of them are decreasing it, the value is negative. So this one has 2 moles going to 2 moles. 2 gases going to 2 gases. This would have 2 bonds to 2 bonds. Okay, none of these really change. So delta S really is not changing much. Okay, so in this case, the delta S would be none or small because you can't calculate it. Okay, now I'm sure there is a delta S value. If you look in the back of the books, you do the math for it, but we're not using the numbers. We're just looking at the possibilities here, and we're trying to qualitatively determine the change. Okay, and so on this one we have 12 moles going to 7 moles, which means delta S is negative because it's going down. We have 6 gases plus 6 liquids going to 1 solid plus 6 gases. So you could eliminate the gases and you've got 6 liquids going. So delta S, again, will be decreasing, so it'll be negative. So the change here is negative. All right, I'm going to pause a second. Pause the video. Try to do this last one on your own. I will continue working at it so you can look at it. So we have 2, 3, and so we have 7 moles on the reactant side going to 8 moles on the product side. So delta S is increasing, so it's positive. We have 7 gases going to 2 gases, no, 8 gases total. So we've increased the number of gases. So delta S is going to be positive. Since you have 2 positive, delta S will be positive. Okay, so you're most likely to get a problem like this on the exam, and you'll be asked to explain your answer. What I did right here is plenty of explanation. You definitely want to include this in back here, because if you just say it's going from 7 to 8 moles, I don't know exactly what you mean by that. That could be a variety of things. So remember, when I go to grade, especially partial credit, I don't know what's in your brain, so if it's not written down, I can't count it. Okay? So that brings us to the last of what is on this first test. This is needed to explain solution formation, else we wouldn't be doing it right now. We'll do the rest of the chapter, as I said, when we do chapter 20.